Humans may have divided different concepts under different subjects, but the physics behind many topics of different subjects is more or less the same. You will be studying Poisson equation and solve a number of problems in electromagnetics, but here we will have a look over a very small part which will be used in our further analysis of semiconductor. James Clerk Maxwell, who is considered founder of electromagnetic theory, gave four equations unifying all the previous work on electricity and magnetism. He studied, researched further, and modified work of scientists who were actually working separately on different domains. We have the Gauss law, according to which closed surface integral of electric flux density is equal to charge enclosed in the volume within the surface. Here d is representing electric flux density and Qn is representing charge enclosed within the surface. S is the surface area. Remember that we are considering closed surface area, meaning that we have to consider total surface area of any three-dimensional object. For example, if we have a cube, then for having a closed surface area, we have to consider the surface area of all the six sides. If we leave any one surface, then we will have a surface area, but that will not be a closed surface area. Therefore, for having any closed surface area, we have to consider the total surface area of any three-dimensional object. Electric flux density within a medium is defined as permittivity of the medium multiplied by electric field intensity. We also know that the charge enclosed in the volume within the surface is equal to integral of charge density with respect to volume. Now let this equation be first equation and this equation be second equation. If we equate these two equations, then we will get by applying divergence theorem, we can write the above equation to be in the form like this. Therefore, we can write divergence of electric flux density to be equal to charge density. By applying divergence theorem, closed surface integral is converted in volumetric integral, and by Stokes' theorem, closed line integral is converted into surface integral. These two theorems are very important in electromagnetic theory, and you might also study these theorems in integral calculus. Now, as we wrote earlier that electric flux density is equal to permittivity multiplied by electric field intensity. Therefore, we can modify the equation like this. We usually take permittivity to be uniform, but it is not necessary. It may be possible that permittivity of the medium is a function of distance x and varies at different points inside the material. Materials which have uniform permittivity are called as homogeneous medium. Therefore, for homogeneous medium, we have just brought the value of permittivity out of the divergence operation as we have considered it to be a constant. So, the final equation comes out to be like this. And this equation is called as Poisson equation. Well, it is one of the way in which we can represent Poisson equation. However, we can also write Poisson equation in terms of potential difference. We know that electric field intensity is equal to negative of gradient of electric potential at the point. And if we replace it, then this is also the Poisson equation. We have only written electric field intensity in terms of electric potential. Otherwise, both the equations are same. However, the first equation is used more commonly in semiconductor devices, whereas the second equation is used more commonly in electromagnetic theory. There is a special case of Poisson equation in which we assume that the net charge density of the volume within the surface is zero. With respect to semiconductors, we can assume that free electron concentration is equal to hole concentration. In such cases, our Poisson equation will modify to, and these equations are called Laplace equation. Similarly, we have studied continuity equation in this subject. However, the same equation with the same name exists in electromagnetics also, which looks little different. In electromagnetics, we have closed surface integral of current density to be equal to negative of the rate at which the charge in the volume within the surface is going outward. Suppose that we have a closed surface area like this. We have assumed the direction of current density to be such that the direction vector will be coming out of the surface and assumed that charge is being supplied to the medium. We already know that the charge enclosed is equal to integral of charge density with respect to volume. Now replacing charge enclosed Qn in terms of charge density rho v, we can write by applying the divergence theorem in the left side of the equation, we can convert closed surface integral into volumetric integral, which will modify the equation to the theorem is called divergence as we take the divergence of the coefficient of the surface integral to convert it into volumetric integral. Now observing the equation, we can write, and this is the continuity equation which is commonly used in electromagnetic theory. Here we do not have any term like generation rate and recombination rate. Otherwise, it is the same equation which we have for semiconductor devices. Another thing that you should keep in mind that the actual formula for electric field is negative of gradient of electric potential. But we usually take electric field to be equal to negative of del V divided by del X. The only reason we take it like this because we are more interested in understanding the concepts, and for making our analysis and understanding easier, we assume that the electric potential is constant or uniform in y and z direction. Therefore, in semiconductor devices, we mostly ignore the other two derivative terms respect to y and z and simply write electric field to be equal to negative of differentiation of electric potential with respect to x. The two equations which we have discussed in this lecture, the one is the Poisson equation in terms of electric field intensity, and the other form of continuity equation will be used in later lectures.